so this is our first question. And I'll give you about 30 seconds to think about it and answer the question. And the way you're going to answer that is through a poll. And let me figure out how to launch the poll. It should, all right, there we go. So the polls will all be of the same format. You will always get this, the same question, which of the following is correct? And you should be able to see the question on your screen. There's going to be one correct answer, and I would expect you to vote within, like, let's say 30 seconds to a minute. Okay, so I'm going to wait for a little longer. See some votes coming in. And as you're voting, try to think about what is, you know, what all are the properties of these different solutions. They're very slightly different from one another, right? And so how do you determine which of these is the correct answer? Answer is really B. And why is that the correct answer? Well, let's briefly talk about it. First of all, we're talking about a force. So force is a vector, right? So the left-hand side should be a vector, but that's no surprise. A, B, C, D, all of them have a vector on the left-hand side. The right-hand side, on the other hand, should also have a vector, right? So that kind of eliminates two of our choices. First of all, this one doesn't have a vector on the right-hand side, and this one doesn't either. So A or C are eliminated. Well, which of the two then, B or D, is correct? And this is where you should remember that it's the name of the law is Coulomb force law. Often it's also referred to as inverse square law. And that inverse square comes from the fact that this is 1 over r squared. Okay, so this is the correct answer. F equals K Q1 Q2 over r squared, r hat. This r hat piece is very important because that tells you that this is a vector. So question number 2 again has 4 choices. This time we are talking about an electric field. What is the electric field due to a point charge Q at a distance r from it? Talking about the electric field due to a single charge, trying to find out what that electric field looks like. All right, so I'm gonna stop the polling here. So let's stop it and polling and share the results. Oh, this time D was the correct answer. And it seems like D is the majority choice. So again, let's just go over it briefly. This time it's an electric field. It's still an inverse square law. It's still a Coulomb force. Out of these 4 answers, only 3 of them are vectors B, C, and D. So we've already eliminated A because it's not a vector on the right side. And out of these 3, Q squared in the numerator is not correct. Electric field is proportional to the charge. And 1 over r is also not correct. Again, it's an inverse square law. So D turns out to be the correct answer. Question number 3. How is electric field and force related? What is the force on a point charge Q if it is placed in an electric field E? And this time the correct answer is F equals Q times E. That was the majority. So we're kind of getting there slowly. Force equals charge times electric field. And this is nothing but a combination of the first 2 questions. So let me go to a quickly go to a whiteboard. So what we're talking about here is that if I have a charge here and there is another charge here, let's say Q1 and Q2, 2 charges, let's say they're separated by distance r, then what is the force between them? That force looks like F equals K Q1 Q2 divided by r squared, r hat. And what does this mean? Well, the Q1 and Q2 represent the charges. R represents the distance between the 2 charges. And r hat represents the unit vector in this direction. So this is r hat, right? And similarly, if I was talking about the other charge over here, this would be the relevant unit vector. So if I had 2 charges situated like this, they will feel a force that is repelling for each of them. So Q1 repels Q2, Q2 repels Q1. Now, in writing any of this, one of the important features that we have assumed is that both charges Q1 and Q2, if I do not tell you a number or numerical value for each of them, then you would assume that Q1 and Q2 are positive. So in this situation, Q1 is greater than 0 and Q2 is greater than 0. The beauty of this formula is that you don't have to assume this. So for example, if in a situation I gave you Q1 equals -1 microcoulomb, and you plug that value in here, then what you would get is F equals negative K 1 microcoulomb for Q1, and Q2 I haven't specified, so I'm just gonna keep Q2 divided by R squared R hat. And this negative sign automatically reverses the direction of that unit vector, right? Because negative R hat is just, if this was R hat, right? Negative R hat is that direction, right? So automatically reverses the direction if I plug in if one of my charges is negative. So that tells me that if one charge is negative, the other one is positive, this force is going to be an attractive force. If both charges are of the same sign, it's going to be a repulsive force. Okay, so that brings us to the point that like charges repel, right? Like charges repel, unlike charges or opposite charges attract. All right, great. Okay, so the next question, and this was, sort of, this will lead us to one of the quiz questions from chapter 21. The force on a point charge Q located at point XYZ is just the coordinates, is 0, right? So it's a null vector, so it's 0. 0 with a vector sign on it because force has to be a vector. What is the electric field at XYZ? Again, you have, this time you have three choices, A, B, or C. A was the majority choice, and it turns out that it must be 0. The electric field must be 0. And why is that? Well, let's go back quickly to our previous question, right? A was the correct answer, F equals Q times E, right? So if the force is 0 and the charge is just an arbitrary charge, it is not 0, well, the electric field better be 0, right? That's the only possible answer that we can get. So the electric field must be 0. A is the correct answer. Okay, now let's do the second part. The point charge Q is replaced by a point charge 2Q at the same point, right? So wherever the Q was located, where the force on it was 0, I have taken that charge Q and replaced it with double the charge. What will happen? What is going to be the now the force on this 2Q charge? Correct answer is still 0. It's A. Why? Because if the electric field is 0, we have found out from the first question that the electric field is 0. The electric field is 0 no matter what charge I place at that point. The net force on that charge has also to be 0. And that's, again, going back to the previous answer, right? F equals Q times E. Remember this, F equals Q times E. If you're ever trying to find the force is the charge that is feeling that force multiplied by the electric field at the location of that force. Okay, so this time I'm gonna ask a question and I'm gonna work this out for you on the whiteboard. Question says that there are two charges, Q1 and Q2. Q1 is located at the origin, but Q2 is located at 0.1 meter, 0.1 meter. So I'm gonna draw that picture. So this is my origin. This is where Q1 is located. And Q2 is located over here at, let's say, X comma Y. Okay, so origin and X comma Y, that's the location of the two charges, Q1 and Q2. Okay, in addition, the problem tells us that Q2 has a magnitude of 2 microcoulomb, so it's a positive charge, and Q1 is -1 microcoulomb. Okay, so I'm going to draw a line through these two charges. All right. And now, again, I want to ask some questions. Maybe we'll do it as a poll. So I want to ask, where out of these 4 points, I'm going to draw 4 points. Let's call this point A. Let's call this point B. Let's call this point C. And let's call this point D. So where out of these A, B, C, Ds can we expect to have a 0 electric field. Question is, where out of A, B, C, or D, where out of A, B, C, or D is the electric field E 0? And try to think about what would happen if the electric field was 0 at a location other than D, or why could it not be the correct answer? So let's briefly see why D might be the correct answer. So if I wanted to figure out what the electric field over A and B are the easiest to see, right? So at A, if I wanted to find the electric field, well, this 2 microcoulomb charge is going to push, the 1 microcoulomb charge is going to pull, so the resultant is probably going to be somewhere in the middle. So it's always going to be a vector with non-zero magnitude. Okay, so similarly at A, the 2 microcoulomb is going to push, the 1 microcoulomb is going to pull, and so the resultant is going to be somewhere in the middle. So these are never going to be 0. So A and B are automatically ruled out. Okay, what about C? At C, the 2 microcoulomb is going to push, the negative 1 microcoulomb is going to pull, but if you look at it carefully, this point is closer to the 2 microcoulomb. So it's going to push really hard. And the negative 1 microcoulomb, first of all, it's a smaller charge and it's further away. So this pull is not going to be sufficient to ever overcome the push from the 2 microcoulomb. So this is also not allowed. So the only other left choice is D, where the 1 microcoulomb is close, so it's pulling pretty hard, right? It's close by, it's pulling hard, but it's a smaller charge. On the other hand, the 2 microcoulomb is pushing. It's not pushing as hard, but it's a bigger charge. So chances are that these two vectors will balance each other and we'll get a 0 answer. Okay, so that's our logic. So we have already determined that D is going to be somewhere in between, below the origin, will be the correct answer. So we would require an x equals a negative answer and a y equals a negative answer, right? Because if this was my origin and this is my x and y axis, you can see that this point D, will have negative for both x and y. Okay, so that's the idea. All right, so now in order to solve this problem, as you can see that the point D lies on the same line as Q1 and Q2, so it's probably easier to solve it by putting it on a straight line first. So I will put Q1 at the origin, Q2 at a distance. What is this distance? Well, this distance, since originally the coordinates were x comma y, this distance is just square root of x squared plus y squared. And on the other side, we don't know this distance yet. We'll try to find it. Let's call this distance L. And we'll start off by saying that this is a positive number. L is a positive number. We just know that it's on the other side of Q1 relative to Q2. Okay, so now let's set up Coulomb's law. So we have to figure out the electric field. It doesn't matter what the electric force on the charge is. In fact, it doesn't matter what the charge is, because if the electric field is 0, as we argued before, the force will be 0. So this could be 1 electron, 2 electrons, 100 electrons. You put whatever amount of charge here. As long as the electric field is 0, the force over there will also be 0. Okay, so we're going to balance the forces. So first what we do is we find the force due to Q2. So in order to find the force due to Q2, we'd have to write K Q2 divided by the distance between Q2 and this charge over here, this point, squared. So that is L plus square root of x squared plus y squared. The entire quantity squared. That must be equal to, so this is the force with which Q2 is pushing it. Okay, now Q1 would be pulling it. So let's for now assign this a negative sign, negative Q1. So we would know that Q1 is equal to 1 microcoulomb, Q2 is equal to 2 microcoulomb in our problem. And the charge that is sitting at this origin is really negative Q1. Okay, so Q2 was pushing it, Q1 is pulling it, and by how much is it pulling it? This should be KQ1 divided by the distance between Q1 and this point, so that's L squared. Okay, so now our next target, go ahead.
I have a quick question.
Yes.
How did you set up that problem? Like, where did we get the L plus the square, I guess? Is that the R?
Right, so that's the distance between, so let's say that we had put an unknown charge capital Q over here, right?
Okay.
So if I wanted to find the force, I would multiply both sides by Q. Okay, so this force, it
Mm-hmm.
looks like KQQ divided by distance squared, which
Yeah.
is what we learned before, right? That's the force.
Mm-hmm.
You could also do it by not putting any charge over here. You could just say that there is no charge over here, right?
Okay.
So that means we are just comparing electric fields. And for electric fields, remember, there's only the charge that is causing the electric field that is in the formula. So for instance, over here, the electric field due to Q2 at that point is just KQ over distance squared.
Mm-hmm.
Okay, does that make sense?
That makes sense.
Do it whichever way you want. Even if you do it with the force, you see, because the same charge appears on both sides, they're just going to cancel.
Yeah.
Okay.
All right. Thank you.
All right. So now what we want to do is we know X and Y, right? So X and Y are known quantities. We also know Q1 and Q2. We also know K. So in fact, since we know K, both sides have K, we can just cancel that. So what we need to find first is L. So how do we do this? Well, L has a square on it. So this is a quadratic equation. So the way to solve this equation, and this is a simple equation, and the way I solve it is we're just going to do an algebra. So first, if you have an equation like this where you have something over something equals something else over something else, well, first you can invert it and write it like this: L plus square root of x squared plus y squared divided by Q2, this quantity squared, is equal to L squared over Q1, right? So this is something that we can quickly do. I've just reversed both sides. And then I'm going to take square roots of both sides. I can rewrite it. We can actually invert both sides of it. And that will look like L plus square root of x squared plus y squared divided by square root of Q2 is equal to L divided by square root of Q1. And since I have taken an inverse and then I have also taken a square root of both sides, I should be careful and I should probably put a plus or minus sign in front of the L over square root of Q1. All right. So far, so good. We still want to find L. Since we want to find L, that means we have to write it as a linear equation in L. And we see that this is really a linear equation in L, which means we should bring all the terms that are dependent on L to one side, all the terms that don't depend on L to the other side. So if we do that, that's quite easy. We get plus or minus L over square root of Q1 minus L over square root of Q2 is equal to square root of x squared plus y squared divided by square root of Q2. This is just algebra. All that I did is took this part, the L over square root of Q2 that appeared over here, to the other side, and then just rearrange things, and that's what it looks like. Okay, and now we can go further, and if I go further, I can pull out the L. So if I pull out the L, this looks like plus or minus 1 over square root of Q1 minus 1 over square root of Q2 is equal to square root of x squared plus y squared over square root of Q2. And I can go further and finally write the expression for L. So that would look like L is equal to square root of Q1 times square root of x squared plus y squared divided by plus or minus square root of Q2 minus square root of Q1. Okay, so do the algebra and you will find this as the result of that algebra. All right, so now comes the important decision. We have not decided. Initially, when I wrote the formula KQ2 over L plus square root of x squared plus y squared, I kind of tacitly assumed that this L has to be greater than 0, because if L was less than 0 and I added L to square root of x squared plus y squared to find this full distance, that would have been wrong, right? So I had tacitly assumed that L has to be greater than 0, which means my final answer should follow that idea, which means that the only answer out of these two, there are two answers because of the plus or minus sign. The only answer that is correct is the one where this negative sign is not there. All right, so this tells me that the only answer that is correct is L is equal to square root of Q1 multiplied by square root of x squared plus y squared divided by q2 minus square root of q2 minus square root of q1. Okay, so that's our answer for L. Now, once we have found the answer for L, in order to find the coordinates, let's call this x1, y1 for D, that's not very difficult, because what we could do is we could go back to our problem and look at this straight line and say, well, since this is a straight line, it has to have the same slope, and the slope of that line looks like m is equal to y over x, but which is also equal to y1 over x1. All right, and now we know this distance, right? This distance is given by this L over here. We have worked it out. Remember, Q1, Q2, and X and Y are all given to us. In fact, in our problem, I think X is given as 0.1 meter and Y is also given as 0.1 meter. These values are probably different for each of your problems. Well, given these values, we can work out L. So we'll move on and we'll ask one more question. Okay, so this question, again, you should have seen this before in class. Apply Coulomb's law to continuous distribution of charges, express the electric field at P due to these small elements, infinitesimal elements of charge at dz. Show the direction of the charge. Again, I'm gonna do this through a poll, and we're gonna, so my question this time is, which of the directions for the electric field at P due to just the segment dz, right? So just this tiny little segment over here, and if I could highlight this, that would be even better. It doesn't look like I can highlight it right now. But so the idea is that if I look at just this segment over here, where my cursor is, what is the electric field at P? What is the direction of that electric field at P? Which of these is correct? A, B, C, D, E, or F? The majority choice was either A or D. So either A or D, right? So either this choice over here or that choice over there. And out of these two, D is the correct answer, it turns out, because whenever you're writing electric fields, remember, if the charge is not told to you, if the magnitude of the charge is not given to you, that means that the charge is a positive charge. And if the charge is positive, the electric field always points away from it. So because the electric field points away from it, at this point, the electric field points like that, okay? The other ones are not correct, of course, because, well, A is not correct because this is, the electric field is not attractive, it's a repelling electric field. And, you know, because D is correct, of course, the other ones are not correct. Okay, so now what I want to do is quickly, I want to write down the electric field at the point P due to that tiny little charge dz, and we're again going to follow Coulomb's law. Just a brief idea that whenever you're writing line charge distributions, in fact, we'll in this class we'll only talk about uniform charge distributions. That tells you that lambda, that's usually referred to as line charge density. Okay, so line charge density, what does this mean? Well, that is the total charge divided by length. Okay, so which means that if I know the length of a segment, then I can find the charge on that segment by just multiplying the line charge density with the length. So dq equals lambda, which is the line charge density, multiplied by dz, which is the length of the segment. Okay, so now I'm going to try to find the tiny little electric field due to that segment at point P. And how do I do that? Well, we will follow Coulomb's law. Coulomb's law tells us that electric field is equal to kq divided by distance from that point squared times some unit vector. So if I want to write dE at the point P, well, what do I have to do? Well, first k, next is q, but we know that the q in this case is dq, which is lambda times dz. And I have to divide this by the distance. And the distance here from that point to that point is given by this symbol r, so we'll call it r squared. The only other thing I have to do is find the unit vector in this direction. Okay, so that unit vector, right now, let me write it as r hat. But that r hat, how do we find that r hat? Well, let's think about it, right? So if I look at this little triangle here, that triangle looks like one side is the z side is just z, the x direction, let's call this direction x. So along the x direction, the distance is d, and the result of that, the hypotenuse is r, which is square root of z squared plus d squared. And we are looking for a unit vector in this direction. So in order to find that unit vector, we can just find the unit vector that is along the direction of that radius vector. So we could just take that full radius vector and divide it by the magnitude of it. Okay, so r hat could just look like, well, this is the x direction, so we will call it di hat, and that's the negative z direction. This was the positive z direction. This is the negative z direction. So the rest of it is just negative z k hat. So that's the full radius vector. Now I have to just divide it by r. And remember, r is square root of z squared plus d squared. So this is my unit vector. So this tells me that dep is equal to k times lambda times dz divided by d squared plus z squared raised to the power 3/2 multiplied by di hat minus zk hat. We have 5 more minutes in class, so we're going to briefly talk about this ring of charge, and we're going to come back to it. So ring of charge, again, let me try to ask a question. So let's see. So the figure over here shows that the electric field vector at the point P due to the charge dq is pointing along this the what appears to me as pink, along the pink arrow, right? But now in a ring of charge, for every dq1 there's a dq2, a charge that is diametrically opposite to it, right? So just like there is a DE1, there's also a DE2. And my question would be, what is the net effect of adding to these two vectors, DE1 or and DE2? Is the net vector going to be along this direction? Let's call that A. Is going to be in this direction, B, in this direction, C, or in this direction, D? What is the net effect of adding these two vectors? So basically the question is, what is the direction of DE1 vector plus DE2 vector? And the majority said it is B, and B is indeed the correct answer. So the correct answer is B right here. And the reason for that is if you look at this picture, the second picture over here, you see that each of these vectors can be resolved into perpendicular components. So perpendicular components either along this direction or along that direction. And you see that the perpendicular components of DE2 and DE1, they are equal and opposite. And the parallel components, those are equal, but in the same direction. So these are going to add up, these are going to cancel. These ones are going to cancel, these are going to add up. So the net result is going to be along the direction of B. So our next task would be to figure out the magnitude of DE, hence the magnitude of this net effect of adding them together, and then integrated over this entire ring. And we're gonna do that. I'm just gonna briefly write DE over here. The idea is to use Coulomb's law, so it's K times the charge, which is dq, divided by the distance square. And if you look at this picture, the distance over here, that distance r, looks like r squared is equal to a squared plus z squared. So I can just write a squared plus z squared over here, right? So that's my distance squared. Multiplied, now I have to multiply by the unit vector. And how do I calculate the unit vector? Again, the idea for calculating the unit vector would be find the net vector and then divide it by the magnitude. So since I have to divide by the magnitude, I'm just gonna write a squared plus z squared over here. And the net vector, well, that's pointing, that has a z component parallel to the z-axis, so that's probably z times k hat. And this next bit is a little bit tricky because this next bit, which is has a magnitude of a, has a unit vector of r hat. Okay, so this r hat is a vector that is pointing like this. It's always pointing radially outward. We are trying to figure out the straight vector that's joining this point A to the point Z. Okay, and so how do we do that? Well, let's say that this is the positive z direction. So one part of this vector, this radius vector, let's call it r vector, the full vector. So that r vector, one part of it is just the vector that is pointing in the z direction. So we have zk hat, and the second part, which is parallel to this a, has a plus a, but this one, it depends on the actual vector itself, depends on where you're located, where this dq is located, and it kind of rotates all over this ring. So depending on where you are, that part of the vector will be pointing radially outward. And so since it's going to be radially outward, I'm going to give it a sort of a r hat, so a radially outward direction to it. And so this is the full vector. The way we can find the component of it, or not the component, but the unit vector, is just by dividing it by the magnitude. So r hat will look like r k hat plus a. Let's give this a different name. Let's call this r prime hat divided by z squared plus a squared square root. Okay, and we just plug it in here, and that's our answer to the DE.